as long as you know what the key features represent, they already give you the equation, so you don't have to come up with that. You just put it in Desmos to graph it, and then you just have to identify the correct key feature. So fairly simple and straightforward. There's not really a lot of extra work you got to do with that. At least in Math 1. Math 2, that's when you may be, having to do more with it by hand. But for Math 1, we only care if you can put it in Desmos, graph it, find the correct key feature. So your I can statement for this lesson is I can model the projectile motion of an object using quadratic functions and identify its maximum height after what? Using. When it will reach it and when it will hit the ground using key features. All right, so again, almost all of this that we're going to be talking about, we're just putting into words kind of what we already talked about in the Desmos activity. So you essentially already know what you should be doing already, but we're just going to give the formalized notes of it. So just to recap, projectile motion is the trajectory and motion of an object or projectile when it is thrown, launched, whatever. All right. So this can be seen with the rockets like we just did. This could be like if I threw a ball in the air. This could be if someone kicked a ball in the air. That's typically how you'll see these questions. Now, in this class, we typically use the quadratics to find the max height of the object, how long it will take to hit the ground, as well as the initial height of the object. So, to find all of that information, we use the key features that we learned back in 8.1 to find these properties. Now, all of these key features, so all the features of projectile motion are shown in this diagram below. So this diagram below is a very nice way to look at the different key features. All right. So whenever we do projectile motion, it's always going to be an upside down U-shaped parabola. All right. And then the only key features we really care about are the zeros or x-intercepts, the y-intercept, and the vertex. Those are really the only key features we care about with this. Now, the biggest three that we care about are these right here. These are the three that we care about. Why do I not care about this zero right here? No, not quite. It'll be a negative zero. And that zero represents what? What does the zeros represent? Or the x-intercepts. What do the x-intercepts represent? The time it took to hit the ground. Right. And we can't have negative time. So in reality, this whole part of the parabola, you can almost scribble it because we don't really care about that part of the parabola. The only part of the parabola we care about is from the y-intercept to the rightmost x-intercept. That's the only part of the parabola we care about. So just to recap, your y Intercept is how high off the ground the object started at. So in other words, it's its initial height. Your vertex, the x value is when the object is at its max height, and the y value is how high is the max height. So essentially, if you looked at it as a point, t and h, t being the time for your max height, h being the actual max height. Now, another question you might be asked, but not often, is how high is the object after so many seconds? All you would have to do for that is, if it asks you how high is the object after blank seconds, so let's say after like 5 seconds, all you got to do is write the equation y equals whatever number of seconds in your calculator. Wait, hold on. Is it y equals? No. Not y, x, sorry. So x equals whatever number of seconds in your calculator. Or you can think about it as t equals that number, because that's the time that they gave you. What would happen is that it would create a vertical line. The point of intersection would give you the height after that many seconds. All right, the y value of that point of intersection would give you the height. All right, so again, if you're looking at the point TH, you care about the H. On the opposite side, if it asked you how many seconds it would take to reach a certain height, you could just put it in as y equals the number and find that point of intersection. So there are ways that you can use Desmos to manipulate what we're looking for. All right. And then lastly, the positive 0 is when does the object hit the ground, or how long is the object in the air. So this is when it hits the ground. So when it hits the ground. All right, so that's just kind of a recap of what we've already discussed with the Desmos activity. Now, the two typical forms that they give us for this function, heads up please, are these two functions. All right, these are like the two typical forms that they give us. This one represents feet. This one represents meters. So if our height was given in feet, we would use the one with the negative 16. If our height was given in meters, we'd use the one with the negative 4.9. And again, they almost always give you the function, but sometimes they're like, hey, if I have a velocity of this and an initial height of this, write the equation. And it's really, really easy because we'll explain that in just a second. So just know that if you see a negative 16t squared, that means it's in feet. If you see a negative 4.9t squared, that means your height's in meters. All right. Now, just so we know what these formulas represent, all right, let's look at specifically the feet one. So this formula right here is the one for when our height is in feet. Now, let's look at the different parts of that function. So the h of the function represents the height of the object after it is in motion. All right, so wherever it is on the graph, whatever that height is. That's also typically your y value of the point. Your t value, so all these little t values here, t represents the time in motion in seconds. All right. And sometimes the variable x is used in place of t, which is completely fine because typically t represents your x value on your graph. Now, V and S. So this V right here, so your B value, technically, if you looked at ax squared plus bx plus c, this is your B value. That represents its initial velocity, or the speed that's initially going at. And S, right here, represents your initial height in feet. All right. So if they ever ask you to write the function, all you have to remember is the negative 16tx squared. That's just always there. And the reason that is because it's a coefficient derived from the value of half the force of gravity on the object. That's physics. It's just explaining why the 16 is what it is. All right. So in physics, this is typically the force of gravity. You may have heard about that in science, but the force of gravity, there's already a velocity for gravity, and it's either 32 feet per second or 9.8 meters per second. That's why the coefficients, or these coefficients, are what they are. That's why we have negative 16 here. It's because of the 3. It's because of this. It's half of that. Now, another thing to note with the initial height, that's also your y-intercept. So you can look at the function without even graphing it and see the y-intercept. Oh, crap. Hold on. It's lagging. Give me a second. There we go. So that's also your y-intercept. And again, with your quadratic application, you yield two different solutions, your positive or negative solution. Remember, none of your solutions for time can be negative. That's what we call an extraneous solution, or in other words, a solution that we can disregard or cross out because we don't need it. All right. Now, in this class, we will typically give you the function already written out, so you don't really have to do any legwork for that. But sometimes you may have to input some of the values in the function. So just know that velocity is typically the value connected to the x, or the singular t, and your initial height is what's typically your constant. And then the one connected to the t squared is always going to be either negative 16 or negative 4.9. All right, that's all you got to remember. So let's at least get one problem in. All right. So a football is punted into the air. Its height, h in meters, after t seconds is given by this equation. So the height is in meters, t is in seconds. So let's just draw a sketch of a problem. All right. So this is another one of those situations where you always want to kind of draw a picture of what's going on. So let's say that your foot is right here at a foot high. All right. And we kick that football. All right. The motion of the football would look something like this. It go up, and then it go all the way back down until it hit the ground of the field. So this would be the ground. And let's say you held the football in your hand like you were trying to punt it. Like everyone knows what, the kickoff is for football, right? All right. They usually hold it in their hand and then punt it. So that's why it's a foot off the ground. All right. Now, how do I know the initial height's a foot off the ground? Why do I know that that's my initial height? Look at the equation. Which value gives me my initial height? The 1. So this right here is my initial height. So that means that my initial height right here is 1 meter, because that's my y-intercept. Now, its maximum height will be about right here. And it hits the ground here. So what I want you guys to do is take a minute, all right, graph this function in Desmos, and that's all I want you guys to do. So graph the function in Desmos. So take a second, graph that function in Desmos. Type it in exactly as you see it, and it should graph it. Or you can replace the h and the t with y and x. Either way. So just graph that equation in Desmos. Yeah. Y'all, put your heads up. Come on. All right. Does everyone have it graphed in Desmos? You may have to zoom out a little bit to see the whole picture. All right. So this is the graph that I had here. All right. And I zoomed out a little bit just so I can see. Now, we know the initial height is our y-intercept, and just to check, that is our y-intercept at 1. So we were correct in that part. Now, let's look at the first question. How high is the ball after 1 second? So remember, we want to write, we're going to find a point of intersection on our graph by writing another equation. What equation would I write? We're looking for when what is equal to 1. Which value does the seconds represent? Your x or your y? So, which variable in the original equation represents seconds? T or h? T. So we're looking for when t is equal to 1. So in reality, we're looking for when what is equal to 1? X or y? X. Because if you look, the t's are replacing what x would typically have. So we're going to graph this in Desmos and then find the point of intersection. So in Desmos, I'm just going to graph x equals 1. And I get this line. Now, the point of intersection is right here. And it asks what the height is after 1 second. What is that height? 20.6. Good. So h after 1 second would be 20.6 what? What's our units? $20.6 what? Height's given in what? Meters. It's up at the top, guys. So just to add that to the sketch, this line right here represents when t is equal to 1, so t seconds. The point of intersection was at the point 1, 20.6. So the height, or h, was at 20.6 after 1 second. All right. Now, look back at your graph and find the maximum height of the ball to 1 decimal place. So if we're looking at for the max height, what key feature am I looking for? The vertex. So for this one, we're looking at the vertex. Which part of the vertex? The x or y value? The y value. So the y value of the vertex. Which is what? So HB equal to what? Say it one more time. 31.6. Good. So if I'm looking at Desmos, I'm looking at my vertex of the graph, and I want my Y value, which is right here, which is 31.6 because they want us to round to one decimal place. 0.6 meters. So your max height is your vertex, which is right here. It's the point 2.5, 31.6. The 31.6 is our max height. So part D asks, when does the ball reach its max height? So it says when, which means we're finding what? Height or time? Time. So we're looking for T. So we already found the vertex. So what part of the vertex are we using now? The X value. So how long does it take? 2.5 seconds. And that is then the, still using the vertex, but we're using the X value now. Lastly, when does the ball hit the ground? So which key feature are we looking for when the ball's hitting the ground? We're looking for the what? We're looking for the positive x-intercept. So take a minute, find that x-intercept. All right, what'd you get for when the ball hits the ground? How many seconds? 0.04? 5.04, got it. So 5.04 seconds, the ball hits the ground. So if I look at Desmos, I'm looking for my positive x-intercept, which is the rightmost one. And it's at the point 5.040 if I round. So this is 5.4 or 040. And this is the time it will hit the ground. All right, any questions on how to find all those key features? All right. Let's try one more, and then we'll call it quits for today. So look at question 4. This one's really quick. So question 4 is one of those where we have to write the equation ourselves. Okay. So a soccer ball is kicked upward from the ground at an initial velocity of 3.6 meters per second. And it's kicked upward from the ground. All right. Now, since it says meters, that means we're using this form of the function. So h is equal to negative 4.9 t squared plus vt plus s. All right, that's the formula we're using. So let's define my variables here. Let's just write the equation first and define our variables. So I need to find what v and s are. So v represents what? V represents velocity. What was my velocity? 3.6. So v is my velocity. So we're looking at 3.6. S represents your what? Not seconds in this case, but your, what does it say on the left side of your paper that S represents? Your initial height. Good. Yeah, they use S because they can't use like I for initial because that means something completely different in math. We kind of avoid variables of I. So S represents your initial height. Now, does it tell you what your initial height is? You sure? The soccer ball is kicked from where? So the soccer ball is kicked from where? The ground. So what's your initial height? 0. So if it tells you that it's kicked from the ground instead of like a height of whatever, that means your height is 0. That's your initial height. So now I'm just going to take these two and plug them in for V and S. So my new equation is H is equal to negative 4.9 t squared plus 3.6 t plus 0. And since we have 0, this could be the exact same thing as H is equal to negative 4.9 t squared plus 3.6 t. So this right here is our equation that represents the situation. So like I said, pretty easy to write. It's just really a formula. You just got to put in like 2 things. So now my question is asking me, after how many seconds does it land? So take a second, put that into Desmos. And which key feature are we looking for? If we're asking for when it lands, we're looking for the x-intercept. So take a second, put it into Desmos, find that x-intercept. All right, you guys get it? Make sure you graph it exactly. So what's t when it hits the ground? How many seconds does it take to hit the ground? Say it again. 4.75. Okay. So we're looking at this one. Guys, you don't need to be talking. If we zoom in a little bit on it, whoa, we're looking at this x-intercept, so 0.735. Okay, got it. So that's not even close to what I was writing. So yeah, 0.74 seconds. That's how long it takes for it to hit the ground. All right, any questions on any of this? So there is a Delta Math for you that's already open. It's very, very easy. It's just all of this stuff, but we only got about 10 minutes left of class, so I'm just going to go ahead and give you your exit ticket. So keep Desmos up because you're going to want it. So just go ahead and knock out your exit ticket, and then we're done for today. And I'll give you guys time to work on the Desmos tomorrow.